Well, thank you to join us here. I think today we are going to talk about how we implemented a blockchain solution with Chainlink and EKS for one of our customer consensus. So first, we are going to go over like what is TrackIt. We are like a AWS partner. We have been in business for 8 years, and mostly our two superpower, it's media and entertainment and app modernization and cloud native software development. We are on 60 people spread between California, France, and Brazil. So I think like, and we have like a very strong connection with blockchain, and we know very well the team at Infura and Consensus for a very long time. I think actually since the beginning of the company, because we used to work in the same company together with the Infura founders. So I guess now we're going to let Luc to present us what is Chainlink and what is like what we did and how we built Chainlink nodes on the top of AWS and on the top of EKS. You want to go, Luc?
Yeah, sure. So hello, everyone. I will start with the basic. So the story of Chainlink started in 2014 by smartcontract.com when they recognized the need for a reliable and secure solution to connect smart contracts with real-world data. In 2017, an ICO has been launched to fund the project. The ICO successfully raised funds, and the project gained in popularity and support from the blockchain community. So what is Chainlink? Chainlink is a blockchain infrastructure that aims to connect smart contracts with real-world data sources. It enables developers to create smart contracts capable of interacting with external data, such as prices, events, weather data, and much more. So we'll go deep into the high-level architecture of Chainlink and explore how it addresses the reliability and security challenges of smart contracts. So let's begin. On Chainlink, there is 3 important component key that run this architecture. So we have the oracles, the smart contracts, and the developers. So let's talk first about the oracles. Oracles are external agents that retrieve data from external sources and they deliver it to smart contracts. The role is vital in providing accurate and reliable data to smart contracts. And Chainlink has a wide range of secure and decentralized oracle that can connect to diverse data sources. These oracles are operated by independent node operators. These node operators are responsible for running the Chainlink software and providing data to smart contracts. So next, we have the smart contracts. So the smart contracts are self-executing programs that run on a blockchain. They define the rules and conditions of an agreement between multiple parties. In the context of Chainlink, the smart contract can be enriched with data from external sources through oracles. And then lastly, we have the developers that play a crucial role in the Chainlink ecosystem because they can create smart contracts and connect them to oracles to access external data. So Chainlink offers a great flexibility to developers by allowing them to use different programming languages to write the smart contracts, such as Solidity, Java, and Rust. And this is great for the community. So now that we covered all the component key of Chainlink architecture, let me explain why Chainlink is so significant in the smart contract ecosystem. So first, Chainlink addresses the problem of trust in external data through the decentralization. Chainlink avoids reliance on a single data source. It also reduces the risk of data manipulation or poor quality. It offers great scalability and multi-blockchain compatibility. It can be used with different blockchains such as Ethereum, Polkadot, and more, allowing developers to use the benefit of Chainlink in various blockchain environments. So next, we'll go through a basic Chainlink architecture. So as we can see on the screen, there is 4 different master nodes, 4 different nodes that Chainlink call oracles that are run by external agents. So on the first node, for example, we have 3 different adapters. So an adapter is a software that will call an API. So we have CoinGecko, CoinMarketCap, and Nomics. And the goal of this architecture is to get the ADA USD rate. So on Chainlink, there is a job that will be run every few minutes and will query these 3 different external points to get the rates. And then the job will create the median of the results. And then one of the oracles will be promoted as a master. And then the master will create the median of the median. And then once the median has been created, the master node will save it to the blockchain. So here is the basic architecture of Chainlink. And now I will let Arthur go through the AWS architecture.
Yep. Okay, so let's now take a deeper look at the deployment infrastructure. So before going deeper in the architecture we designed, we looked at the possibility. We look at our possibilities. So AWS already published an article on how to deploy Chainlink on the cloud, but they decided to deploy Chainlink directly on an EC2 instance. And on our side, we wanted to have a very resilient deployment to showcase what can be done on AWS. So hosting the Chainlink nodes directly on the EC2 would have meant limited redundancy and no scaling capability. So still, the AWS way has some great advantages because it's definitely way easier to understand than using an orchestration tool. And also, as the infrastructure is way simpler on the blog, it results in a decreased monthly cost. And however, for all deployments, we wanted to showcase the ultimate Chainlink deployment on AWS. So that's for those reasons that we choose to go with an orchestration tool rather than directly on EC2. So one of the first choice we faced regarding the architecture was to decide how we would manage our Chainlink deployment. So in the big pictures, to deploy the new node, Chainlink provides a pre-built Docker image. And on AWS, you have multiple ways to host Docker image. So we considered 3 options. So the first one would have been deploying every component on EC2 instances directly, like AWS did, or deploying it on ECS, or deploying it using EKS. So for the reason where I gave in the introduction, the first choice of EC2 was removed from our consideration, and we only really considered ECS or EKS. So ECS is the AWS managed services to run containers on AWS. So it can use either EC2 as backend or Fargate, which is a serverless compute system, which allows for having an entire serverless container system. Fargate is also not a choice we consider for a long period of time because it's not really intended to be used for 20 hours, 7-a-day system, because it's have the tendency to be very expensive and is more designed for high scaling and very short-lived tasks. So our second choice was EKS, which is the Kubernetes service entirely managed by AWS. And like ECS, it also has 2 compute backends. So you can either go with EC2 or Fargate. And for the same reason, we also excluded Fargate from our consideration. So in the summary, we really ended up with 2 choices. which was either ECS on EC2 or EKS on EC2. Yep. So in order for us to make this decision between EKS and ECS, which if you look at the internet, it's quite a common question when it comes to host containers workload on AWS. So we had to look at how Chainlink works. So under the hood, Chainlink nodes are entirely self-contained, so they only need a single container to run, but they do still, however, need some external components. So for a Chainlink node to be really useful, it needs to be connected to one or more adapters. So each adapter is kind of a gateway between Chainlink and the external API, such as CoinMarketCap or Nomics. And all those adapters run inside their own containers. So this changes a bit the complexity of the deployment, because from a single container, we are now entitled to a nano number of containers, because each time we need to add some adapters, we will need to add some containers. And using ECS, it would have been more complicated for us to make the adapters deployment configuration replicable. And we would have been severely limited for configuring the network security between the node and the adapters. So another point was regarding the monitoring and the surveillance. So one of the key parts for high availability is to be able to see and analyze the status of our deployments. And for that purpose, Kubernetes have standard systems such as Prometheus for metrics collection. And it can be used in combination with Grafana for displaying the metrics in forms of collection of graphics. So as those components are standard, they have already been integrated natively into Chainlink. And as we will show in the demonstration a bit later, you can draw a dashboard with Grafana with a lot of information regarding the states of your node. And the benefits of going with Kubernetes instead of ECS is that we can take advantage of the large ecosystem already present. And for example, to deploy Prometheus and Grafana in our cluster, we used Helm, which is some kind of package manager for Kubernetes, and does greatly simplify the configuration required for having a deployment that works out of the box. And our last point we had considered the high availability standard. So in general term, ECS brings fewer controls over the availability configuration, and Kubernetes has been built from the start and with every update with high availability in mind. So this came to be a particular point for our Chainlink deployments, because as I will show you in a few minutes, making Chainlink resilient to failure was a bit tricky, and we had to use features only available on Kubernetes. So for all those reasons, we choose to go with EKS over ECS. And so now for our orchestration platform, we had to design the general infrastructure inside it. So for the data storage, we have two types of data to store. The first are the Chainlink, the data provided by Chainlink, which require database. So the documentation specifies that this database must be a Postgres database. And fortunately for us, AWS already provides an entirely managed service for relational database, so that includes Postgres. And as we didn't want to go through the configuration step to have our own self-managed cluster, we went with RDS because it was way faster. And the second type of data we had to store are block storage. So it's mostly for Prometheus and the Grafana dashboard to save their own data. So we needed a block storage system. And once again, AWS provide multiple ways. So there's the first one, which is the EBS, the standard elastic block storage, which is nothing more than a standard volume storage. And there's also EFS, which is elastic file system. And it's an NFS storage system. So in our architecture, we went with EFS because it has high availability by default, because it can be accessible from multiple availability zones, where our EBS are only attached to a single AZ. So we'd have been stuck and we have been forced to place all our EKS nodes inside a single AZ. On top of our data storage block in the diagram, we have our EKS control plans that controls the two EC2 instances on each side, which represents our EKS nodes. Those nodes are spread across two availability zones for high availability purpose. And for security reasons, all this architecture is not reachable from the internet. So every component is secured inside a private network. And the component inside the network can access internet through a NAT gateway, but the internet cannot reach the inside of this network, except for one thing, which is the Chainlink nodes. It does have a port that needs a public IP, which is used for peer-to-peer connection. And for that, we attach an elastic IP directly on the nodes, and the elastic IP is managed by the AWS load balancer controller inside Kubernetes. So all of that is standard components available directly natively with EKS. We also added a client VPN for private access for debugging and just accessing the inside of the web UI, Grafana, and everything. And for the other AWS services we used, those are very standard. We use KMS for key management, secrets manager for storing the sensitive configuration information, and Route 53 for creating private DNS that can be resolved automatically once you are connected to the VPN. So let's now take a look at the architecture inside the Kubernetes cluster. One of the most interesting and complex points we had to tackle down was to design how we could deploy the Chainlink node in such a way that it would survive an entire AZ failure. The major difficulty in that was that Chainlink cannot be horizontally scaled. So each instance of the Chainlink node takes a lock on the database, and it makes it impossible to start multiple nodes at the same time on the same database. So to provide still this high availability mechanism, we updated the Chainlink container to provide two health check information. One says when the container is working fine and the Chainlink process is just running. And the second one says when the database lock has been acquired and that the node is operating normally. So thanks to this update, we are now able to use a very specific feature of Kubernetes, which is the liveness and readiness probe. So those are two different health checks. The first one, the liveness probes, allows to give the information to Kubernetes when a container is working fine, but is not yet ready to serve traffic. So it's generally used to say when a container is starting. And the second one, the readiness probe, gives the information that the container has finished starting and it's now ready to receive traffic. And one of the difference between those two health checks is how Kubernetes reacts in case of a probe failure. So if the readiness probe fails, the pod, the container running inside, will be removed from the load balancing pool, and that just means that the traffic will be stopped sending it to it. And if the liveness probes fail, Kubernetes will trigger the redeployment of the failed container. So we use this mechanism for our Chainlink deployments, and we use the liveness probe to tell if our container is running fine. So if it fails, it's just replaced. And we use the readiness probe to tell which of our Chainlink replica has taken the lock on the database, and it's the one that must receive the traffic from the load balancer. So in summary, when everything is working fine, we should see X number of Chainlink nodes, and all of them should succeed their liveness probe, but only a single one should succeed its readiness probe, which is the active one and the one where we are sending the traffic from the web UI. So the rest of the configuration is pretty much classic. We use services behind ingresses to manage incoming traffic to the cluster. We use deployment to manage our container, with the exception of a stateful set for Chainlink, because we wanted to have this replica and rescale feature of the replica sets we can have with the stateful sets. And we use the config map for configuration keys and secrets for sensitive configuration. And I'll now let Jean-Gaël do the presentation.
Okay, so I'm going to present the demo part. In this part, we are going to look at the configuration, do the configuration, and then deploy. Then we will be able to go into Chainlink. So first of all, we created two Helm charts to deploy the Chainlink node and its external adapters. We are also using Prometheus and Grafana Helm charts. And we are using Terraform to configure the whole infrastructure. And Terraform is also going to deploy the Helm charts and will take advantage of SOPS to decrypt our secrets. We also created a Github repository for this demo, which is called AWS EKS Chainlink white paper. And on the README, you will be able to look at the different steps to deploy this infrastructure. So the first thing you want to do is to clone the repository on your machine, and then you will be able to open it with your favorite editor. When you have that repository, you should see something like the following. So first of all, Helm charts folder, Chainlink Helm, which is going to contain the different Helm charts we created, so Chainlink and adapters, but also some configuration files for Grafana and Prometheus. Secondly, you will have a Terraform folder that contains all our Terraform configuration, and a NOM folder that contains the TF vars that will be used for our different environment. And finally, you will be able to find the secret folder inside the TF1 and clear secrets YAML file. So both contain encrypted for the secrets folder, and in the clear secrets .yaml file, you will see the decrypted secrets. So usually we never purge the clear secrets file, but in that case, it's just an example that you can use or duplicate. Before diving into the Terraform and SOPS configuration, we will need to create our Terraform backend. So the Terraform backend defines where Terraform stores its state data files to keep track of the resources it manages. And this backend is composed of two AWS services in our case, so an S3 bucket and a DynamoDB table. You can create this backend using the AWS CLI or directly via the AWS console, but make sure that both are in the same AWS region and that the DynamoDB has a string partition key named locid. And we are now good at configuring our Terraform backend and providers. So open the providers file. And here we will have to update that file to put our Terraform backend. So here I will have my bucket, my S3 bucket, which is AWS EKS Chainlink TrackIt. I will set the region to US3 because this is where I created my bucket and my DynamoDB table, and I will also put the name of my DynamoDB table. I will also change the AWS provider region to US3 because this is where I'm going to deploy the infrastructure. We also need to have a KMS key. In the AWS region, you previously chose to encrypt and decrypt our secrets using SOPS. Once we have our KMS key, we are able to dive into our SOPS configuration. First of all, we need to fill our secrets in our clear secrets.yaml file. So you can put it directly in that YAML file or duplicate the file, then fill the value. It's completely up to you. But just remember to not to purge this, this file because this is where our clear secrets will be. And so before encrypting our secrets using the SOPS CLI, we need to export our KMS key that we created as an environment variable. And we will also create a dev folder because we are going to deploy a dev environment. And then we will be able to encrypt our secrets in this dev folder using the SOPS CLI. So the previous command should have created an encrypted secrets.yaml file that looks like this one that contains all our encrypted secrets. And we are now able to configure our Terraform variables by creating a new TF vars file that I'm going to call dev because we are creating a dev environment, and we are going to fill some values. So first of all, the KMS key ID. So this is the one we use to encrypt our secrets with SOPS. I will change my environment to dev. And for that one, for the ACM certificate, you won't need it because in this demo, we wanted to keep things simple. And we decided not to include the part where we deployed the load balancers. I will remove and comment, the AWS host roles. So this is the one that is used to connect to the EKS cluster, but I'm not going to use a role to connect to the cluster. I'm going to use instead the AWS host users variable to connect to the cluster using my IAM user. I will let the default VPC values, except for the region, because I'm choosing a US 3. Then we will change the ETH URL with mine. So this is one that I get from Infura. For the Chainlink domain name, we won't change anything since we won't have any load balancer. We don't need it. The user email is the user we are going to use to connect to the Chainlink UI at the end. The Chainlink ETH ID, you can find that one when you create your ETH URL. So mine is 1, and I will change Chainlink dev to false because this is an environment variable on Chainlink, and we have a mainnet. The ETH URL is on mainnet, so we are going to put false here because this is not on testnet. We are now almost done to deploy our infrastructure. Before doing that, we can grab our terminal and go inside the TF folder, then run the Terraform init command that's going to init our Terraform and verify that the Terraform backend is good. We are also going to create a new workspace because I want to have my environment, my dev environment in a proper workspace. And we are now able to apply using our tfvars file that we just created before. So before deploying, you can take a look at the different resources that will be added, changed, or destroyed. And you can type yes and enter whenever you are ready to deploy. So my deployment took 13 minutes and it deployed 85 resources. So we are now almost done to access our Kubernetes cluster and our Chainlink UI. We just need to use the AWS CLI to update our kubeconfig with the Kubernetes cluster we created to be able to access it. When this is done, we can use the kubectl command line to list the pods. So as you can see, we have our Chainlink node that is running, and the other one that is running but not ready. So we can copy the Chainlink that is ready, and we will port forward. Use the port forward command from kubectl to forward the 6688 port on our machine, and we are able to access Chainlink UI in localhost. We will need our user email and our password that we define in our clearsecrets.yml file to connect. Unfortunately, we cannot create the bridges with our external adapters automatically. We need to create them manually in the Chainlink UI. To do it, we need to have our ES ports, and you can find them in the values.yml file of the adapter Helm chart as EA port. So as you can see here, I'm looking at the crypto compare port, and I'm going to use that port to create the bridge. So in the Chainlink UI, go in the bridges section, and we can now create our first bridge for the crypto compare adapter using the right port, and we should be ready to go and maybe creating our first Chainlink job. We also wanted to show you how it looks like in a production node. So here it's a Chainlink node in production from a client. We can take a look at the list of the jobs. We can then see the job overview, the different jobs runs, and some details about the different runs that we have. We can also take a look at the different nodes that we have in the node section. And so here we should have only one node. And we can take a look at the different bridges. So as you can see, there is a lot of other bridges that you can create. Here is the Grafana dashboard that we implemented. This dashboard was given by Chainlink, but you could also create your own one. On this dashboard, you can see Chainlink node metrics, such as the node balance, different container uptimes, and also blockchain metrics. So thanks for listening, and if you have any questions, feel free to ask.